Okay, so let's carry on with where we left off. So today we'll finish up this chapter, chapter 10, and then go on to the next chapter on Datapath. Okay, so you can see that we are transitioning from the software. So we started off with C programming, okay, then we moved on to assembly language, okay, and then we started to look at how to encode assembly language in the binary bits. Okay, and now we are transitioning more and more into the hardware. Okay, so we are moving away from the software and moving towards the hardware side of the processor and the lower level logic blocks. Okay, so just a quick recap of where we left off during last lecture. So we talked about this concept of the memory address. Okay, so a processor can have or for a processor to communicate with memory, we have the address bus and we have the data bus. Okay, so we need, when we have KB address bus, that means we have 2 to the power of k addressable locations. Okay, and n-bit data bus is the amount of data that I can transfer, okay, to and from the memory at any point of time. So, of course, when you are designing a system on your own, you try to match everything, okay? Match everything as in what? That means if my processor has registers that are 32-bit, okay, so if I have a processor where all my registers are 32-bit, then I would also want to, then my data bus would also be 32-bit, okay? And I will want to make sure that I can access memory at 1 word at a time. Okay, if I have, for example, a 32-bit processor, okay, but the memory that I choose, okay, is the memory side. There's only 16 bits coming out. Okay, 16 bits coming out from the data bus. That means what? If I were to use a 16-bit data bus memory and I try to interface with a 32-bit data bus processor, can it work? The answer is yes, it can work, but it is a lot more troublesome, correct? That means each time I want to load my register with a value from memory, I need to do 2 cycles, correct? Because each time my data bus can only hold 16-bit data. Okay, so even though it is possible to try and mix and match, okay, different lengths of bus and memory and so on, if you match everything, then your life is easier. Okay, so if your processor is 32-bit, then you know that your processor's data bus is also 32-bit. So you probably want to interface with a memory that also has a 32-bit data bus that supports. Okay, and then we talked about the Indianness of your data. Okay, so this is very critical. Okay, when you have multiple bytes of data representing a larger word. Okay, so if I have a word which is 32-bit, okay, and I have 4 bytes of data, how is this data arranged? Okay, and this plays a significant role when you deal with different boards. Okay, so for example, if I have a Arduino board and I want to transfer data to a RPi, okay, then you realize that your RPi Indianness and your Arduino Indianness is different. Okay, so when you try to send data over and you do not reconcile this rearrangement of bytes after you receive the data, then everything is going to be messed up. Okay, so it's very important you understand the format in which data is stored in memory. Okay, so in your MIPS processor, we only talk about 3 different addressing modes, as you have seen. One is your register, which means you have 2 source which are registers, and then your destination, okay, is also a register. The other one is your immediate, where you have 1 source register and 1 immediate value, and then you have your target register or destination register, and the other one is your displacement, which is your base plus your offset, and then you access memory. So these are the 3 main addressing modes that you have in your MIPS. In other type of processors like the CISC processors, you have a lot more variation because CISC processors generally can directly take from memory and do arithmetic. Okay? Whereas MIPS, you can see that you need to load the data to a register before you can do your whatever processing that you need. Okay, so the standard operations in an instruction set. So you can see that the most common ones are what? Your data move instructions. Okay? Why? Because effectively, originally everything is in your memory, correct? So before I can do anything, I first need to take data from memory, move it to my processor, do the necessary arithmetic operations, and then I write it back to memory. So effectively, if you look at it, there is a lot of memory transaction going on while you are executing code. And of course, once you move data to your processor, so data move is bring it into your microprocessor. And after you do that, then you need to, or you can do all your arithmetic operations, logical operations, whatever you need, and then you finish everything, and then you move it back to your memory. And when you write your program, you will have a lot of subroutines, you will have a lot of branch, okay, you have a lot of loops and so on, okay. And of course, things like interrupt and graphics and string we are not covering here, okay, but these are other things that your processor can handle as well. Okay, so this is a sort of a snapshot of the frequently used instructions in the processor in terms of the code that it executes. So as you can see, we always do a load, okay, and in the end we do a store. So load and store always a lot, okay. Why is it store less? Because you don't always need to store everything that you load, correct? Sometimes you load and then you just make use of the data for some processing, and then that data is actually the output. Okay, take for example, you want to play a MP3 file, correct? Okay, so you need to load all the data coming in from your memory. After you load all the data, what do? You just process, but you don't write it back. All right, after you process it or you do any filtering to it, then you pass it to your output module, which is a speaker, to play out the song or whatever. So there is a lot of load instructions. Okay, conditional branch and compare. Why do you have a lot? Because in our code, we always have a lot of loops, correct? And then you have a lot of if-else statements. Okay, so that generally all our code you see a lot of these loops and if-else statements. So that translates to a lot of conditional branch and compare instructions when you translate from C to assembly. Okay, the other operations that you see here, all these are sort of dependent on what you're trying to do. All right, so depending on what kind of operation you're trying to do, then that kind of arithmetic will be used more and more frequently. So this is just a estimate only, okay? Okay, so now the last part of this chapter is about instruction format. Okay, so let's look at what are the different types of instruction format. In terms of instruction length, okay, we have two types. One is called variable length, the other is called fixed length. In MIPS, everything is fixed length. All right, that means all our instructions are fixed at 32 bits. Okay, and this is used mostly in your RISC type of processors. Whereas if you want to have variable length instructions, okay, like your Intel, then you have the concept that different instructions can have different length of instruction, okay, which makes it a bit more complicated, correct? That means your processor must be able to sort of know how to fetch and how much to fetch, correct? So for example, if I say that this is maybe 8, 16, and 32, okay, and I say that I have a variable length processor. So when I go out to the instruction memory and I fetch the instruction, how many bits do I fetch? Do I say I fetch 8-bit, do I say I fetch 16-bit, or do I fetch 32-bit? All right, so you need to do a lot of playing around, correct? So you can say that, okay, maybe I fetch 32-bit, correct? And then I look at the first 8-bit first to see whether this is a valid instruction, correct? So if this is a valid instruction, then out of the 32-bit, this first 8-bit become one instruction, correct? And then I look at the next 8-bit. So if the next 8-bit say that it is not a valid instruction, then what do? I try to look for the next 16-bit, correct? And then I try to sort of manipulate from there, Okay, so it becomes a lot more complicated from your processor because it doesn't really know upfront whether this is already an instruction. Okay, so I need to do a lot more upfront processing to look at the bit pattern and then decide whether this is a valid instruction. Whereas if I have a fixed length like your MIPS processor, that means I know that every time my program counter points to an address, I fetch 32 bits in. Correct? So it's a fixed length, so there's no confusion there. So in terms of architecture, design, it's a lot easier and faster to decode your instruction. And also it simplifies other things like pipelining and so on that we will study in the future lectures. Okay, there's also hybrid instruction where you can have variable and fixed. So these are just to show you the variations that we can have. Okay, so what are the instruction fields that so far we have observed? Okay, so we know that opcode is there. Okay, and why is opcode important? Because opcode tells the processor what type of instruction this is. Right? So by looking at the opcode alone, I will know whether this is going to be an R-type instruction, is it going to be I-type instruction, is it a jump instruction, and so on. And depending on the opcode, I also need to look at how many operands I have. Okay, because R-type instruction, then you talk about 3 operands. Alright, I-type, you have 2 plus 1 immediate field and so on. Okay, so the operands, the data that it represents also is related to the opcode that you have. Okay, so in terms of your size and type, you can say that for fixed length instruction encoding, everything is quite clear and quite upfront, okay, compared to a variable kind of length where you do not know anything upfront yet. Okay, and for 32-bit architecture, okay, we know that how many bits is going to represent what. So this is defined by the processor. So that is why in MIPS we say that character is 1 byte, okay, integer is 4 byte, and float is 4 byte, double is 8 byte. Okay, in some system you may have an integer that can also go up to 8 bytes. Okay, so it depends on what kind of architecture is underlying the whole processor. Okay, so let's look at how we can do encoding. Okay, so in terms of encoding, so when you say encoding, what are we trying to do? Okay, so in terms of encoding, we are trying to see how to represent the instruction in a binary format, okay, that you can fulfill all the instruction the processor wants to support. Okay, so different processors may support different set of instruction, depending on how they're designed. So for example, in MIPS, you saw that if you look at the Boolean operation, logical operation, it does not have NOT. Correct? It does not have some of the operation. Why? Because you can achieve NOT with some other operation and so on. So these are some of the things that you need to look at. Okay, so what are the issues? One thing is the code size. Okay, if I decide on a particular encoding format, how big is my code going to be? Speed and performance is related to the overall architecture design, and the complexity of the design also relates to how much the hardware is going to sort of cost eventually. Okay, and things to be decided, okay, number of registers, number of addressing modes, number of operands. Okay, so if you were to carry on and study hardware description language, okay, one of the things you will probably do is to design your own processor. Okay, so when you say design your own processor means what? So for MIPS, you know that you have 32 registers, alright? And each register is 32-bit. But now if I tell you, you go and design your own processor, you decide everything, then what will you do? So you need to make some decision, correct? How many registers do I need for this processor that I'm going to design? Okay, so if I say I want 8 registers, okay, if I want 8 registers means how many bits must I have for my register field? I must have 3 bits, correct? Okay, so previously for MIPS, we say we have 32 registers. Okay, so that is why for my RS, RT, everything is 5 bits. Okay, so now if I say you can design your own processor and your register is you need to have 32 register, only 8 register, which means that now you only need 3 bits, alright, to specify which register you're talking about. And that means what? That means if I still have my full 32-bit for my full instruction, okay, and now I say instead of 32 register, you only need 8 register for your MIPS. That means you free up how many bits already? You free up potentially 6 bits, correct? For RS, RT, and RD. So now this additional 6 bits, okay, what are you going to do? Okay, so you can think of other things that your processor might be able to do. Okay, so these are all part of your design. So if you are asked to maybe design your own processor, which you are not doing in this module, don't worry. Okay, if you are ever going to do it, then these are some of the questions you need to ask yourself, correct? Okay, and like number of addressing modes. So the addressing mode that we saw in this MIPS processor is what? R, I, and J. Okay, so if you design your own, what are the other addressing modes? Do I want to support direct memory access and arithmetic operation at the same time? Okay, so things like that. Okay, so there's a lot of factors to consider, okay, because the number of registers, the size of the code, and so on. Okay, so let's look at what are some of the encoding options. Okay, so these are some of the possible encoding options that you can have. So in terms of fixed, which is what we saw for MIPS processor, you know that it's roughly like this. And this is not the actual one, but it's something like this. That means you know that the first certain number of bits is your opcode. Then you have a certain fields after that to specify the register you're talking about. And then maybe if it's an R type, then I have some other function field. If it's an I type, I have an immediate field and so on. So there could be something else that I add here. But I know that eventually all the instructions are fixed. Okay? Whereas the other option is a variable instruction length. Okay, variable instruction length means different instruction can have different length. Okay, so I need to look at my opcode, okay, to sort of decide and know upfront, okay, if this is the opcode, this is specifying a subset of instructions that are 16 bits long. If I have a different type of opcode, then this represents instructions that are 32-bit long. Okay, so it varies. Okay, so of course fixed length presents a much more interesting challenge. Okay, how to fit multiple sets of instruction type into the same number of bits. Okay, so let's look at an expanding opcode scheme. Okay, to show you just the idea of how this whole thing works. Okay, so let's assume that I have a 16-bit fixed length instruction. Okay, that means my whole instruction is now 16 bits. Okay, and I have two types of instructions. Okay, so one type is I have two operands, and each operand is 5-bit. The other type B is one operand of 5-bit. So let's assume that I take the fixed length encoding scheme. Okay, if I use the fixed length encoding scheme, that means I say that, okay, since I have type A, I need 5-bit for each operand, and I have two operands. So this 5-bit and this 5-bit will take up 10 bits, correct? Because type A instruction, I have two operands. So 10 bits is already used up for type A instruction to satisfy these two operands. And that means I only have 6 bits left, okay, for the opcode. Okay, and now if I say that this is fixed length, that means all my type of instructions would have the same opcode, like how you see for MIPS instruction. Right, in MIPS instruction, you have the same bit length reserved for the different type of instructions. So in this case, if type A is 6-bit, type B must also be 6-bit, correct? Because it's a fixed length instruction encoding. But in type B, what do you see? I only have one operand, correct? So in type B type of instructions, when you say type means what? So type means could be maybe type A is talking about all your register type instruction, and type B is maybe talking about your I type instructions or something like that. So it's a different classification of instructions that you can have. So looking at the fixed length opcode scheme, what do you see? You see that type B will have 5 bits unused. Correct? Type B will have 5 bits unused because type B only requires one opcode and one operand. Okay, it's because type A requires 2 operand, I need to have the 5 bits there. But in type B, that 5 bits is wasted, it's not being used. Correct? So now, what can we do if I were to try to maximize this 16 bits that I have with a variable instruction length idea or expanding opcode idea? Okay, so in the expanding opcode scheme, what is the idea? The idea is the instruction length remain the same. Okay, the instruction length remain the same. So I'm still dealing with the same 16 bits here. Okay, but what is changing is the opcode length. Okay, so in type A, I have 6 bits, and in type B, I make use of the full 11 bits. So what do I have now? It means I don't have any wasted bits, correct? Okay, I don't have any wasted bits. But how do I make sure that I do not confuse myself with type A and type B? That means what? That means the first upper 6 bits of type A must be such that the upper 6 bits of type A and upper 6 bits of type B here, okay, there must not be a match. Correct? Then only I can differentiate immediately what is type A, what is type B. Because if the upper 6 bits of type A and upper 6 bits of type B happen to have the same, then your processor will get confused, correct? And not be able to decode correctly. So what I need to do is, I need to reserve one instruction where the upper 6 bits is set aside for type A alone. And then everything else I can use for type B. Okay, so I have only one type A instruction, okay, where the upper 6 bits is fixed, okay, and reserved for type A, and then the remaining is 2 to the power of 6 minus 1 multiplied by 2 to the power of 5. Okay, why 2 to the power of 5? Because this is 6 and 5 here, correct? So here I have all the 2 to the power of 5 combination, and here I have 2 to the power of 6 but minus 1, because this 1 is reserved for the type A instruction. Okay, so in this way I can maximize my 11 bits to represent the most varied number of instructions possible, okay, for my encoding. Okay, so this is just one idea. So this is not implemented in MIPS, okay, but this is just to give you an idea on how the different type of ways you can still play around if you want to have a fixed instruction length encoding scheme, okay, by playing around with the number of bits you use for the opcode. Okay, so that brings us to the end of this chapter. So in this chapter, basically what we look at is the different type of format in terms of your architecture. Okay, so in your tutorial you will go through some examples again. So you will actually explore this in more detail. So in your next week's tutorial, you will actually explore these 4 architectures a bit more to sort of have a better understanding how these 4 different architectures actually work. Okay, and why one architecture may be better than another architecture and so on. When you compare things like memory usage and code size and so on. Okay, so that's the end of this lecture 10. Okay, so let's move on to the next topic, lecture 11, which is on your data part. Okay, in this chapter, data part, we are going to go fully into the hardware layout and design of your processor. Okay, though we haven't covered some of the hardware or the actual logic gates so on in detail, which we will cover in the second half, we will introduce them along the way. Okay, so some of the hardware blocks, as you see them, we will explain what it is. Okay, so you understand how it works. Okay, so we're going to look at the whole thing, how to build a processor from scratch. Okay, what are all the different blocks and how everything comes together. Okay. Okay, so there are 2 parts to a processor, 2 main parts to a processor. One is called data part, the other is called control. Okay, data part is basically how the data flows through the whole processor. Okay, data, when we say data, in a sense, the instruction. Okay, the whole 32-bit instruction, how that 32-bit instruction is sort of decoded to get the data that you want and make the complete the arithmetic or logical operation, get the result, and then what do you do with the result? Okay, control is the telling us which are the devices to access and manage the flow of the data as it goes through. Okay, so they are both interlinked together, so they both work together to make the whole processor work. Okay, so let's look at some of the subset of the instruction that we're going to look. Okay, so in this set of slides, we are only looking at 3 types of instructions here. One is your arithmetic and logical. Both arithmetic and logical operations is the same flow. The same flow. Data transfer is a different flow, and branch is a different flow. So we're going to look at 3 different flows. Okay, when I say flow means we're going to look at how these 3 different types of instructions will actually be executed by the processor as it goes along. Okay, shift and jump is not discussed. Okay, shift and jump is not discussed, but you can think about it. Okay. Okay, so effectively, what does your processor do? Your processor actually does only 3 things continuously again and again and again, which is fetch, decode, execute. Fetch, decode, execute. So these are the 3 things that your processor is doing endlessly from the time you power it up to the time you power it down. Okay, so these are 3 things. So when you say fetch, the first thing that you must fetch is what? Your instruction, correct? The first thing you need to fetch is instruction, because that is the thing that tells the processor what to do. Okay, and where do you fetch it from? You fetch it from your memory. Okay, so you need to fetch it from your memory. Okay, so if you look at your system, you have your processor connected to your memory through the address bus, correct? Okay, and through the address bus, what do you do? So you need to tell the processor that right now my address is in this line. Okay, go and fetch this address into my processor. Okay, this week's lab, you will actually get to see that when you get introduced to the SPIM. Okay, when you look at Qt SPIM and you write your code, you will actually see that it occupies certain address location. So your instruction has certain addresses, your data has certain addresses, correct? Okay, so when you do this week's lab, you will actually get to have a better understanding of the address aspect of it. Where is this address stored? Is in your PC or program counter. So the program counter is a hardware block inside your processor that keeps track of where is the instruction that is to be executed next. Where is the address? Where is this instruction stored? So once the instruction is fetched in, so when I say I fetch an instruction, say add, okay, S0, S1, S2. Okay, let's say I fetch this instruction in. Next, I decode. How do I decode? I look at what? Okay, so the first thing I need to look at is my opcode, correct? Okay, so from opcode, I will know roughly what type of instruction it is, what I need to do, and maybe I also need to look at what? The function field. Correct? Your R type, there is the last 6 bits, which is the function field, correct? Okay, so by looking at the opcode and maybe looking at the function field, I will know what type of instruction this is. Next, after I know what type of instruction this is, I may need to do an operand fetch. Operand fetch effectively is what? That means, where is the data? Okay, and this operand fetch is actually what? Your register, correct? Okay, where your data is stored. So if I say S1 and S2, then the operands are basically your S1 and S2, the data inside register S1 and S2. And after I get the data from S1 and S2, then I execute. So execute means I must activate the ALU block, correct? Okay, so I know that, okay, if this is add instruction, I must tell the block that this is an add instruction, go and do this operation for me. And after I get the result, what must I do? I must take the result and put somewhere, correct? So there is a write back stage. So the write back stage is after I finish the whole add operation, I need to write back to my S0 register. Okay, so this is effectively the whole cycle that your processor goes through. Okay, so let's understand a bit about how this thing is going to play out here. Okay, so these are all the cycles here. So fetch, decode, execute, and write back. Okay, fetch and decode, we already know what it is, because fetch means you go from you take the address, send it to the address bus, your memory will reply back with the instruction in that address. Okay, so that is your fetch. Your decode is looking at your opcode. So that is the same whether it is R-type instruction, whether it's a memory access, or whether it's a branch instruction. That part is the same. Then subsequently there are changes. Why? Because if I talk about operand fetch, in this, your operands are both in my registers, correct? If I talk about load word instructions, one operand is register, but one is immediate. Okay? And in this branch equal instruction, both my operands are also in my register. So which means what? That means I now need to take the operands or the data that I need to deal with from different places, correct? It could be register, or it could be register plus value. Then I execute, okay? So execute wise, what do I need to do? So in this case, I'm doing an add operation, correct? So this add instruction only make use of my ALU block, correct? Okay, but let's look at this. In this load word, what do I need to do? I need to make use of ALU. Okay, I need to make use of my ALU block here. Plus, I also need to do a read from memory. So I need to do two things here, correct? My ALU must also be triggered to do an add operation. And after I do the add operation, I must still go to my memory to take the data, correct? So I need to do two things here in terms of execution. Same thing for BEQ, I need to do two things. I need to check whether my operand 1 and operand 2 are equal, which is branch if equal. And then what do? Then I need to update my program counter to the new address, correct? Because I need to know whether the branch is supposed to be taken or not taken. Okay, if the branch is not taken, then it should be the new PC address, correct? If the branch is going to be taken, then I need to jump to a new address, correct, which is not the next line in the code. Okay, so I need to do two things here. And what is the end result of each of the instruction? If I look at add instruction, the end result is a value stored in a register. If I take a load word instruction, ultimately I'm taking a data in a memory and putting it to a register. That is the end result. And for branch if equal, the end result is my program counter is changed. Alright? So what do you see here? You see that it's very challenging. Why? Because only the first two stages is clear cut. Only the fetch and decode is standard. Correct? But every other stage is very different for different type of instructions. Correct? And we not even look at shift instruction, we not even look at jump instruction. Correct? So excluding those two already, we can see there's a lot of differentiation between what the processor should be doing for different type of instructions. Okay? So let's look again at how we can apply this to the MIPS. So the fetch, as you can see, is the same. We read from the current PC value. The operand, again, is the decode and operand fetch is actually the same now. Why? Because in all three cases, your value is either in the register or is already given in the instruction, correct? The value is either in the register or already given in instruction. So it's either one or the other, either in the registers or already as part of the instruction. Okay, and the ALU, in this case, for example, both of this I need to do an add. Here I need to do a equal check. And a memory access is only for load word or store word. Correct? So other type of instruction, I don't need to do memory access. Okay, and then the result is depending on the type of instruction. So this is, again, we are trying to break down the steps. Okay, so we understand how we translate each of these steps into the hardware that we are going to see now. Okay, so let's look at the view of the designer. How are we going to design the processor, okay, from the beginning to the end? Okay, so the first thing that we need to have is a program counter. And what is a program counter? Is basically a register to program counter to fetch instruction from your memory. And the PC is automatically incremented by 4 after the next instruction. Okay, so let's look at the hardware. Okay, so this is the hardware for the program counter. Now what do you see here? This program counter is, okay, it's a 32-bit register. Okay, and what comes out? What comes out here is the address I want to read. So the address could be starting from maybe 0x00, okay, all the way to FFFF. Okay, so assuming this is your full memory range, correct, for a 32-bit address. Now, of course, your instruction memory is not going to occupy the full address, correct? Your instruction memory is only going to occupy a section of your full address range, correct? Why? Because your full address range is everything that your processor can. I've drawn this before. So basically, if you look at your memory design, okay, so memory design is done by who? The system architect, correct? The system architect must come out and decide, okay, for this processor, I have a 32-bit bus. So for 32-bit bus, this is my address range. For this address range, where do I keep all my subsystem? Okay, most cases, your instruction memory, if you're talking about a standalone system, will start from address 0. Okay, why address 0? Sorry? Yes, but basically why? Because 0 is always there. You always know a starting point, correct? The starting point is always 0, but you do not know the ending point, correct? Okay, so by having a, I'm not sure whether you've heard this term before, reset vector. Have you heard this term before, reset vector? Okay, so maybe some of you have heard. Reset vector is basically where should my processor start executing from when I press the reset button, correct? When you reset your handphone, when you reset some device, how does it know where to go and start executing the code from? So it must be a fixed point, correct? It cannot keep changing. Okay, so most processors architecture is such that the reset vector will usually be address 0. Okay, so you know that that is a common address to start from, which means what? So what must I put at address 0? What should be the hardware here? The hardware there should be my what? Your memory, correct? And which memory? My program memory or your instruction memory. Because that will not change, correct? That is permanent, it's fixed. So you know that when I reset my system, I go to address 0, I start to take the first instruction, and then I start executing. Okay, so no matter what happened, I press the reset button, this thing will always start, correct? Because I know I need to jump to address 0, and then from there I start executing the first instruction. Okay, so you know that you need to have this much program memory. And you're not going to have the full program memory all the way, correct? That will be too expensive. So you need to have other memory, you need to have other subsystem, and so on. Okay, so this instruction memory here is maybe from 0000, maybe up to some memory here. Okay, maybe FFFF. Okay, something like that. Okay, you will only occupy a certain section of your address space. Okay, it will not be the full address space. So when your program counter gives out a value, what is it giving out? It is telling the instruction memory which instruction I want to fetch. So we know we start from 0, for example. Okay, so when I put the value 0 out, what will happen? So in address 0 here, okay, so in address 0, which is the first line, there is an instruction, correct? Okay, so let's assume that maybe that is an add instruction. Okay, so that add instruction will then come out of my memory to where? To my processor. Correct? To my processor. So the program counter job is to provide the address to the instruction memory, and the instruction memory is to provide me with the data in that address, which is actually the instruction, correct? Okay, and that instruction is taken and sent to my processor to do the next stage. Okay, and you can see here that when the address goes out, it also goes to another block called the adder block, okay, which is nothing more than generating a PC plus 4. Okay, so you can see that when the processor is executing one line, I already increment and standby the PC plus 4 already. Okay, that means I assume by default that the next instruction is the next line. Right, that is the default behavior. Okay, so this is memory is nothing more than sequential circuit. We will cover more of memory later on. Okay, of course, for memory you still have clock, which is not shown at the moment. That means when I provide the address, okay, so if I provide the address here, I also have a clock. Okay, so when you talk about digital logic or digital circuits, you have combinational circuit and you have sequential circuit. Okay, combinational circuits are circuits which will just perform the operation without any clock. That means you don't need a clock. Whereas a sequential circuit requires a clock. Okay, and what does that mean? That means if I provide an address, whatever address I provide here, it will not do anything unless the clock trigger comes in. Okay, so unless the clock trigger comes in, then the device is activated to give me a new output. If there is no clock, then nothing comes out. If there's no clock, nothing comes out. So there is a clock, but it's not shown here to make it simple for you. Okay, and what does it do? It gives you the instruction at the address. Okay, so this gives you an idea. So in each address location, now this is the address. Okay, all these are the addresses. Okay, and in each address, there is one instruction which occupies 4 bytes. It's 4 bytes. That's why you can see that here to here is all 4 byte, 4 byte. Okay, now we talk about the adder just now. This adder is a combinational block. Okay, a combinational logic block does not require a clock. Okay, so the moment I say it's combinational logic, that means there is no clock involved. Which means what? That means when I provide an input, the hardware will just trigger and I will generate the output. Okay, so there is no clock involved. So in this case, I'm trying to add two numbers together. Okay, A plus B, I get the result A plus B here. Okay, in our case, this B is fixed at value 4, correct? So it just becomes PC and PC plus 4 as the output. Okay, so of course, when you look at this clocking, it may seem like we are trying to read and update the PC at the same time. Okay, why I say that? Because it seems as if we are trying to take the PC here, but at the same time, we are immediately updating. Because I say this adder block does not have a clock, correct? If your adder block does not have a clock, what does it mean? That means the moment the data come in here, I will immediately generate PC plus 4 and come back here, correct? Okay, so that part is immediate. It's almost an immediate circle. Okay, but because of the clock mechanism, you will not change the data that comes out from your memory. Why is that so? Because you only need to change the data at the next clock cycle. Okay, so when this clock comes in, what happens? At this clock, okay, your PC is 100. That means the instruction at address 100 is being read out. Correct? It's being read out from your instruction memory. But immediately, once your PC becomes 100, within a very short period of time, okay, within a very short period of time, it becomes 104, correct? This time is basically the time for the adder. It's just a very short, probably a few nanosecond kind of time to do the add operation, and then you get the output of PC plus 4. But even though the PC plus 4 is there and you become 104, and 104 is already here. 104 is already at the memory, but your memory will not react. Okay, because it is a sequential block. So your memory will only react at the next clock cycle. Okay, so that's why we do not need to worry that the PC has already been updated. Okay, even though the PC has been updated, your clock only comes in, or when your clock comes in the next cycle, then the 104 is read out. Okay, and then from 104, you become, so once you become 104 over here, then you become 108 and so on. Okay, so you can see that your instruction will always be immediately incremented to the next. Okay, but your memory will not react until the next clock cycle come in. Okay, so that is how we are able to make sure that even though your program counter change, your memory will not change and give you the next instruction yet until the next clock cycle. Okay, so in this case, we are talking about rising clock. All your systems, when you design, you will either design them to be either all on rising clock or all on falling clock. Okay, so in this case, we are assuming that the whole processor is triggered on the rising clock of the edge. Okay, so every time there's a rising clock, you will trigger the next cycle and so on. Okay, once I get my instruction, then I can go on to the next stage, which is decoding. Okay, so let's look at decoding. Now I know that for my decode stage, okay, when I look at my instruction, I have 3 registers. Okay, so for example, if I take my add instruction, okay, that means inside my instruction encoding, I have my RS, RT, and RD, 3 registers, correct? Okay, and these registers are all stored inside where? Is again inside a hardware known as a register file. Inside a register file. What is a register file? Okay, a register file is nothing more than a small memory within the processor to hold all this data for you. Okay. So in this case, your register file is nothing more than just 32 registers stacked one on top of another. Correct? So this register file, if you think about it, is just 32 registers. A total of 32 registers, correct? Okay? Because you have 32 registers in your MIPS processor. And what I need to do is, I need to be able to tell which register I want to access. Correct? Okay, so if I want to access register S1 and S2, then I need to tell them that I want to read from 2 registers here, which are S1 and S2. Okay? So let's look at this. So in my R-type instruction, okay, I need to read from 2 registers called RS and RT. Okay, and then I also have another register called write register, correct, which is my S0 in this case. Okay, so let's just look at R-type for now, so we are clear. For R-type instruction, there are 3 registers, 2 to read from and 1 to write to. That means when my instruction come out, I need to tell the processor which are the 2 registers I want to read from and which is the register I want to write to. And each register is 32-bit and you have a total of 32 registers. Okay. There is also another signal here called register write. These are all part of your control signal, which we will do in the next lecture. Okay, but control signals are what? That means you want to tell the hardware how to behave. Okay, not every instruction is going to write to a register file, correct? Okay, not every instruction is going to write to a register. Okay, so for example, if I were to do a store word instruction, okay, if I do a store word instruction, okay, let's say I do a store word instruction. In this instruction, what will I do? I will take some data that is in S0 and write to some address, correct? I'll take this data, write to some address. There is no writing to a register here, correct? Okay, there is no writing to a register here. So I do not always need to write back to register. Only in some cases I need to write back, some cases I do not need. So I need to know when to do it, when not to do it, and so for that I have a register write. So this is a control signal. Okay, where does this control signal come in? When I want to write, I must supply a 1. If I supply a 0 means I am not going to write to the register file. Who is supposed to give me this 1 or 0? The control block. The control block, okay, we are not looking at that now, but just have this in your mind that there is another block called a control block which will tell me whether I need to write to this register file or not. Okay, so let's look at this. Just have a glimpse, then we go for a break. Now look at this add instruction here. So in this add instruction, this is my RS, this is my RT, and this is my RD. Okay, so what does that mean? I want to read from register 9, register 10, and write back to register 8 after I do the add operation. So from here to here, we already know how to do it, okay, in terms of instruction encoding. Now, okay, so this is your RS, RT, and RD here. Okay, RS, RT, and RD here. Again, this is your opcode. So what does that mean? When your instruction is fetched from your memory, okay, the bits 25 to 21, which represent RS, must come into my read register 1, correct? Because I need to read from this register. And the second register I need to read from is the RT. So bits 20 to 16 must come into here. And I know I need to write back to a register which is register 8, which is RD, and that is in bit 15 to 11. Okay, so this 5-bit, 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 directly from my instruction, I can map it to my hardware, correct? So I know which are the two registers to read from and what is the register to write to. Can? Okay, so we will go for a break. Okay, when we come back, we will look at how this whole instruction is completed by the processor. Okay, so I know it's a very dry and sometimes confusing topic, but don't worry, you will get there. see that if you look at it from half cycle, when the clock comes in, it's already the new value, correct? The PC value for it. Okay? And then your instruction that comes here, the IN here, is the next value, right? Okay, that means throughout this clock cycle, my PC already become 104. Okay, but then it doesn't do that. Okay, why? Because this one is 104, which means that this one also become 108. Right?
And there are like two ways to go, right? Because if we go up here, the instruction is like going in the instruction. Right?
So PC is holding this 104, alright? But then what is here is now 108.
Alright, afterwards. But where does like the PC is 100, instruction is 104?
That means whatever value that PC is going to turn the instruction value, I already have the next value here. Because I already have done the add and done that.
Add is faster than
Yes. Add will always happen immediately. That's why you still need to wait for the next clock.
how long is the recall process? Is it like this whole line?
It's definitely going to be much shorter than
Point is that every time like the error was going up the addition is performed.
yes. I don't know. The addition is performed regardless of the clock. As long as there's a value there. So even though 104 is presented here, then what is here? The register 100, correct? Okay, so for example now we need this cycle. Okay, so it become 104, correct? And 104 means this one become 100, correct? But 104 is still here, correct? That means this add operation is still considered going on. It's just that the value never changes.
So, I want to ask you a question. So, instead that when we use like DQ, can it count how many lines
Based on the PC plus 4.
yeah, it's just faster. Question is on the job. Will the PC counter be here?
Before you execute the jump, your PC is already here. Yeah, but because you do a jump, then you will adjust to that.
I just want to ask, like, I did send an email before, but this is on Monday. I wasn't able to come on Monday, and on Monday I had my lab and my tube, so I wasn't able to come with them. So is it alright if I can
This Monday.
this Monday, yeah.
Yeah, you can attend something else.
Yeah, just attend.
Then you must tell the teacher that you're from another class,
Yeah.
so they will know where to come.
No, it's just that because then if the lab asks for like confirmation from you, like whether you have actually.
Yeah, you just say you talk to me.
Okay, yeah.
I don't get this example. Why when there is 8 registers, there will be 8 bits more?
6 bits more.
Why is this?
Because rightfully, okay, so right now we are having 32 registers, correct?
Yeah.
Okay, so for 32 registers, it's 2 to the power of 5, correct?
Yeah.
So you 5 bits each. So 8 register means
5 bits each for.
2 to the power of 5 is 32.
Oh,
correct?
yeah.
So for 8
This
register,
is it
the number of bits
like the
to
RTRS?
yes,
Yeah.
number of bits to represent the register.
Okay.
So if I say 8 bits means it's 2 to the power of 3, correct?
Yes.
That means I only need 3 bits. So if from 32 register, if I say I scale down to 8 register, it means from 5 I go down to 3.
Yes.
That means I save 2.
2.
So for 3 register I save 6.
Oh. So it's like there are.
So for example right now, you look at my full 32 bit here, correct? My opcode is 6 bits, correct?
Yeah.
So previously I say 555.
Yes.
But now I'm saying is 3,
Oh.
3, 3.
But also the left one is.
So now
like
I have
function.
additional plus 6 bits because I have shift and function too, correct?
Oh, yeah.
But now I got another 6 bits. So now you can think of
Try to
what can I
use-
use these 6 bits for?
Okay, thank you.
Okay, so let's resume. Okay, where are we now? So we are trying to understand how your processor is going to take an instruction, okay, and how is it going to use the different bits. Okay, so we know that every instruction is encoded in 32 bits. How am I going to make use of the 32 bits to tell the processor what to do, where is the data, what operation to complete, and where to store the result? So I need to tell the processor all this information, correct? So we are going to now look at the simple add instruction and try to figure out how this instruction, the 32 bits, propagate through the processor to tell it what to do, okay? So what we know so far is we know the translation of the instruction to the opcode. So this is the 32-bit opcode. Okay, now in this 32-bit opcode, we know that this is a R-type instruction, which means that after the opcode, which is the 6 bits, the 5-bit, 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 which is bit 25 to 21 is representing RS, 20 to 16 is RT. And these are the two registers that I need to read from, correct? In this instruction, RS and RT represent two registers to read from. And all the registers are inside this hardware known as register file. Okay? So effectively, you can see that I have 5 bits here. Why 5 bits? Because your register file is total how many? Total is 32, correct? That means if I want to select any of the 32, I need to specify 5 bits, correct? If I say if what goes in is 0, 0, 0, 0, 1, that means I'm talking about register 1, correct? And what is that means I'm supposed to go inside here, take the data in register 1 and bring it out. Okay? So what am I providing here? This 5 bits is something like the index. Which register am I talking about? Okay, I have 32 registers in my register file. Which register am I talking about? So that is what the 5 bits is for. And that is already inside your instruction. Okay? So this 5 bits here is representing which register I'm talking about. So when this 1001 goes in here, what must come out? The content of register 9. Whatever is the content inside this register. Same thing over here. When this value 10, 1010 goes inside here, read register 2, the content of register 10 will come out. That is the decoding stage. So what we are trying to do is now we're going to decode this instruction. So to decode this instruction, I need to know where is the data coming from. Okay, and this instruction tells me that I have two data and both of them are from the register, correct? Both of them from the register file, and which register I'm talking about is already specified in the instruction as specific bit pattern, correct? I already know that this bit to this bit is representing RS. I already know that this bit to bit, this bit is RT, correct? So I take these bits, transfer them to my register file, telling the register file, these are the registers that are going to read data from, so I get this content. And the last one here, this is your destination register, bit 15 to bit 11. That means what? That means after I finish the operation, I need to write back to this register, correct? I need to write back to the register. That means what? After I still need to do what? I still need to do an add operation, and this one must come back where? To my write data here, correct? Okay, after I complete the add operation, which we are going to look at now, that result must be written back to my RD, correct? My destination register, and that is already specified as my write register. And in this instruction, what should the value of my control signal be? 1 or 0? Should be 1, correct? Why? Because this instruction, in this particular instruction, I need to perform a write back to a register. In this instruction, I need to perform a write back to a register So the register write bit should be 1. So now let's look at carry on, and let's look at a different instruction now, the add immediate. Okay, so for add instruction we saw this. Okay, now for add immediate, what will happen now? So for add immediate, when we translate, what do we get? The same bit here, 25 to 21 is your RS, which is this. Okay, and now this is your RT, 20 to 16. And the remaining 16 bit here is your immediate value here. Now you can see that it gets complicated. Why does it get complicated? How do I map the bits? Can I follow the same mapping? Okay, can I follow the same mapping? The answer is cannot. Okay, why? Because for 25 to 21, which is my RS, okay, value 22, that is fine. So I read the content of register 22, alright? Okay? But 21, the register 21 is the write register, correct? In this I-type instruction, this RT is mapped from bit 20 to bit 16, correct? Okay? In my previous R-type instruction, 20 to 16 is a source register, correct? In R-type instruction, bit 20 to bit 16, when I read, okay, in this R-type instruction, this is your R-type. When I read bit 20 to 16, it is a read register, correct? But in my I-type instruction, okay, 20 to 16 is a write register. Okay, so I cannot follow the same mapping. Okay, it is wrong. Okay, so what must I do? Okay, and you can see that 15 to 11 now also doesn't make sense. 15 to 11 does not make sense because 15 to 0 is a 16-bit data. Correct? 15 to 11 does not hold anything. It's just part of the immediate value which you can't do anything with. Okay, so I need to now make some changes to the processor now to accommodate the I-type instruction. So what do I need to do? Okay, so the 25 to 21, bits 25 to 21 will not change, correct? Those bits are still mapping to my RS. Okay, so this is RS. So that one, there is no change. But what I need to do is, I need to use a multiplexer to choose the correct mapping. Okay, so let's look at this to understand a bit more how it works. So what is a multiplexer? Okay, multiplexer is, okay, maybe I go to the next slide first, then I come back to this. Okay, a multiplexer is nothing more than to select one input from multiple input lines. Just like how at home you got one TV, but you got your Singtel box, you have a StarHub box, you have a Netflix, you have your Android box, you have everything, correct? Then you keep switching, and you don't know what to watch, correct? Okay, the same thing. So you have multiple input, and then you can select which one should be sent to the output. Okay, and how do you select that? Is basically through the control lines. Okay, and the control line is basically m bits, and based on that you have so many number of outputs. Okay, so for example, if I have 4 inputs, okay, if I have 4 inputs, how many control bits must I have? 2 bits, correct? Okay, so it is 2 to the power of 2 must be equals to 4. So if I have 8, then it must become 3, and so on. Okay, so the number of control lines that I have should be raised to the power of 2 to know how many input I can support. Okay, and based on the control line, I will select which one will be going out. So at any point of time, only one of it. Okay, one of it will be selected to go through. Okay, so that is the idea of a multiplexer. Okay, so let's come back to this. Now that I have a multiplexer in, okay, what is this multiplexer going to do for us? So this multiplexer is now going to decide whether bit 20 to bit 16, okay, should be sent to my read register or should be sent to my write register. Okay. So if this was a R-type instruction, so in an R-type instruction, okay, then what will I say? 20 to 16 should go to my read, alright? Okay, and if this was a I-type instruction, then 20 to 16 should go to my write. So that is where your control signal come in, called the register destination control bit. So just like how we have a register write to decide whether I need to write back to a register or no need to write back to a register, I now have a register destination control signal. And the purpose of this register destination control signal is to determine whether bit 20 to 16 is actually a source register, that means a reading register, or is it a destination register or write back register. Okay, so the register destination bit will be generated from a control block, which we will see next lecture slides. Okay, so the control block is responsible for generating all these signals for us. These are all the control lines. Okay, so the control block will take the opcode, take the function field, do everything, and then decide, okay, this is a R-type instruction. So if R-type instruction, then I say this one is 0 or 1, okay? So it depends on how you configure. Okay, but basically your register destination is the one that will determine whether this fella will go through or this fella will go through. Okay, so that is the idea of your multiplexer here. Now the other thing is your data. If I look at this instruction again, what do you see? I have a add operation that I need to do, but in this case, one of it is my read register, which is the obtained from my bit 25 to 21 here. Now the second one is my immediate value here. So it means what? That means I must look at the last 16 bit, okay, which is here, and also transfer that as my data to do the operation, which is the add operation. So what do I need to do? I also need to do a sign extension of my data to become 32-bit. Now this one we covered in our tutorial 1. Okay, why do we need sign extension? Because your ALU is already 32-bit ALU, correct? So your immediate data you translate from 16-bit to 32-bit, so you can directly feed it to your hardware block. Now, when I extend this 16-bit and I send it over, I now must have another control signal with another multiplexer. Why? Because I know I need to do an add operation, but in this case, I must now differentiate between register add or immediate add. So when I look at the opcode here, I must know that this is a immediate instruction. Correct? So if this is an immediate instruction, then it is the 16-bit data that must go through. If this was a normal register instruction, then it is the register file data that will go through. Okay, and that is from the ALU source control signal. So the ALU source control signal, what will it do? It will tell the processor that for this particular operation is the second data. Is the second data going to come from my register or is it going to come from the 16-bit immediate value? Okay, it will do the correct selection for you. That is your second multiplexer here. So what do you see we are trying to do? We are trying to come up with the initial design, correct, which was based on the R-type. And from the R-type, we are slowly modifying it to adapt to I-type. correct? Okay, and of course when you add J type and you add shift and so on, then there is more and more modification. Okay, so the idea is we start with a very simple architecture and then we slowly enhance it step by step to support a wide variety of instruction. Now let's look at the load word instruction. So this is where we are. This is where we are in terms of the structure so far. And this structure that you see right now, as it is, it already supports your R type and it already supports your I type. Okay. Now let's see how we can support a load instruction. Okay, which means you need to do a memory access. Correct. But before I do the memory access, I must do a add operation here, correct? So I need to have a source register, I need to add with the offset, and that will give me the output that I want. Now what do I have here? For load word instruction, this is my RS, this is my immediate, and this is my RT. Is it the same as just now? Is the same, correct? So you can see that the load word instruction actually is already supported with the current architecture as well. Correct? Why? Because my RS is here, okay, which is 25 to 21, okay, which means it comes out here. And I need to add with the immediate, which is already supported here. And my ALU source, as long as my ALU source knows that for this style of instruction, I need to select the immediate value, then this and this can go to my adder block, correct? This and this can go to my adder block. So it's already supported. So I do not need to actually modify anything. Okay, for load word. This current architecture already support my load word. How about a BEQ? So in BEQ, what am I trying to do? I'm trying to check whether this register and this register are equal. Okay? And then what must I do? I must now generate a new PC based on this offset, correct? I must now generate a new PC value based on the offset. Okay, you must understand that when I fetch this instruction and my processor is executing this instruction, I still have not known whether the branch is to be taken or not, correct? Okay, so when I fetch, I do not know. When I decode, I do not know. When I execute, then I know, correct? When I execute the instruction, then I will know that this branch is supposed to be taken or not to be taken. Okay, but from what you saw earlier, your program counter, the moment the value come out, it already increment by 4, correct? By default, it already increment by 4. So now let's see what we need to do here. So in this, we need to calculate the branch outcome and the target at the same time. So what is the branch outcome? Branch outcome means whether this is true or false, correct? Okay, so that is the branch outcome, whether I'm going to take the branch or not going to take the branch. And at the same time, I also need to know the target address. Okay, I also need to do the calculate the target address, which is based on the new PC value. Okay, so how do I tackle this? Okay, so before we go to that stage, let's look at the summarized view of the decode stage. Okay, so the first stage is what? The first stage is your fetch. Your fetch is your PC, go to your instruction memory, get the instruction, and go to your decode stage. And in your decode stage, what are you trying to do? You are trying to look at your RS, RT, RD plus your immediate value to know what is the flow of data that you should go to your register file. Okay, so this RS here is fixed. This RS here is fixed. So it's either it become RS, RT, and RD, or it could be RS and this is RT, and then this whole thing here become a immediate. Okay, so there are two variations that we need to support. Okay, so this is just the summarized view of what we saw just now, and this whole thing works because we are able to generate the appropriate control signals here. Okay, by generating appropriate control signal, we can control how the data will flow through the processor. Okay, now let's look at the third stage here, which is the ALU stage. Okay, so we saw two stages. This is the third stage with the ALU. So the ALU stands for arithmetic and logical unit, okay, which is also the execution stage. Okay, so all your add instruction, subtract, or shift, whatever that you're supposed to do, everything in most cases is done here. Now let's look at what we're going to do in the ALU stage. So for your ALU to work, basically you need to supply it with two input, correct? Your two input parameters here, and you need to tell the ALU what to do, correct? So from the decoder stage, you already have the two operand, correct? We saw that from the decoder stage, we have the two operand, and the two operand is what? It's either register plus register, or register plus immediate value here. So these are two possible input that your ALU can receive, either register and register, or register and immediate. Now these are two possible input. So how do I tell the ALU what to do? Is it an add? Is it a subtract? Is it a AND OR operation? How do I tell it? There is another control signal called ALU control. So this ALU control will tell your ALU block what operation should I perform. Should I activate the adder block? Should I activate the shift block? Should I activate the OR gate block? Whatever. Okay, so this ALU control will tell us what ALU operation I need to perform. So you have two input 32-bit numbers, and you have one output here, which is the result. So the result here is 32-bit here, and at the same time you also have another output here called is0. So this is0 is a 1-bit signal to indicate whether the result is 0 or not. Okay, so this is a 1-bit signal to indicate. So this gives you a idea to check immediately whether two numbers are equal or not equal. Okay, so that's why they have this additional is0 output. Okay, to check immediately whether the output of it is equal to 0 or not. So for your branch, you can straight away look at this signal to decide whether a branch should be taken or not. Okay, and you can see that I have a 4-bit control for my ALU, which means what? I can support how many instructions? 16 instructions, correct? Within the ALU block. Okay, so this is only a subset because we are not having so many variation of instruction. Okay, so your ALU block, as you can see here, these are some of the instructions that you support. Okay, and why is it this way? When you look at the next lecture, you will understand why do we have the bit pattern in this way. Why we never just say 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, and so on. Okay, why we have a particular bit pattern. Okay, so there's a reason for it. Okay, now let's look at this addition of the ALU block. So far we saw until here. Okay, and now we are adding the ALU control block. Okay, so what is the difference? Actually nothing much, because we know that in the first stage, which is the decode stage here, you already have two 32-bit numbers here ready for the ALU operation. So in this execution stage, all we are going to do is we need to pass the data to my ALU, let it do the operation based on whatever I supply here to my ALU control, and after that I get a result. Okay, so for non-branch instruction, no problem. So this 9 and 10, for example, I do an add operation, the result come out here already. The result is readily available. Okay, and the ALU control will be generated by the control unit. Okay, and this control unit basically will look at the opcode, look at the function field of your instruction, 32-bit, and then decide what ALU control bit to send over. Now let's look at branch instruction. So for branch instruction, we can say that we can use the ALU to compare two registers. Okay, so for BEQ and branch if not equal, all we need to do is to compare two register value and we check whether the E0 is set or not. Okay, so we're going to see how we can use the E0 bit, okay, and at the same time calculate the new target address. And remember, for branch instruction, we need to do two things. The ALU must tell us whether the two numbers are equal or not equal, and at the same time, we must also generate the new target address to jump to. So now it looks a bit more complicated. Okay, so what do we do here? Okay, so this 16-bit here, okay, after I assign extend become 32-bit. This is based on the number of lines to jump, remember? And when you do your tutorial, this number is what? Is the number of lines to jump, correct? But in terms of bytes, you must multiply by 4, correct? Okay, so that is why we have a left shift 2-bit here. So the immediate value that come out, you have to remember that you are specifying number of lines to jump, correct? But each line is 4 bytes. So to have the effect of the 4 byte, multiply by 4, we left shift by 2-bit here. So this is the multiply by 4 here. Okay, and I take the PC plus 4 and add. So now you can relate back. Just now, previously when we do the instruction encoding, why I say you must take PC plus 4 and then look at the number of lines. Alright, why? Because PC plus 4 is hardware driven. The hardware automatically generate the PC plus 4. We cannot control it. Okay, so that is why we put the number here based on the PC plus 4, and then you add or subtract the offset. Okay, and what do I do here? I take PC plus 4, add with this new value to give me a new address. Okay, and this is the if branch taken. Okay, so if the branch is taken, then that is the address I need to go to. If the branch is not taken, then it is just PC plus 4, correct? If the branch is not taken, then PC plus 4 must go through. If the branch is taken, then it's PC plus 4 plus the offset and multiply by 4, which is also what you did in your tutorial, remember? Okay? So you can see that I will generate two possible addresses right now, correct? One is PC plus 4, the other is the new branch address. And then I will make a selection based on a control signal called PC source. Okay, so this control signal PC source will then tell my processor, should I take the branch or should I not take the branch? So that is the implementation of the branch. Okay, so the PC source is the control signal to select either one, either PC plus 4 or the branch target. Now let's look at, okay, so PC plus 4 will be PC source, you will know when, will be updated after the ALU stage, correct? So after I get this answer here, then I can generate the PC source. And that link is not yet discussed here. So after the ALU stage, when I get the result of whether the comparison is 0 or not 0, then I will know what value to set for my PC source. Okay, to decide whether it's the next instruction or the new branch instruction. Now let's look at the memory stage. Okay, so we are in the fourth stage. So we did fetch, decode, ALU, and memory. So in memory stage, what is the last thing we need to do? We either need to read from memory or we need to write to memory. Okay, so we need to have a memory address that is calculated by the ALU stage. Okay, why? Because if I say a load word S0 4 S1, so this is actually a add operation, correct? Which is performed by the ALU block. Okay, so the final memory address that I'm going to access is only available after my ALU stage. Okay, and after I get the final address, then I need to go to my memory, read from my memory, and then get the data back. Okay, if it is a store, then when I get the memory, I write to the memory location. Okay, so that is the two possible things. So let's look at memory now. So in memory is the same concept as instruction memory. Only thing, instruction memory, you don't write to it. You don't write to it. There is no write data in instruction memory because your instruction is supposed to be fixed, correct? Instruction is supposed to be fixed. But in your data, your values are always changing. So you can read, you can write. So you have two control signals here, memread and memwrite, to tell the data memory whether I need to read from memory or need to write from memory. Okay, so when I complete the ALU stage, I get a result. Okay, and this result is actually giving me what? You have to remember, for memory type instruction, the result is always giving you the address only, correct? Okay, why? Because if it is a load word, then I will take the data and put into my register, correct? If it is a store word, then the write data already come from my register. So the ALU operation is only giving me the address, nothing to do with data. ALU operation only giving me the address. For load word, I would read from the address and write it back to register. If it's a store word, the data is already in the register, correct? Then I just write it to memory. So the ALU operation, that result is only giving me the address that I need to access. Okay? Now what do I do? So the memory is again the same idea. It's just a sequential memory block, okay, with certain address bus and certain data bus. Okay, and you have two control signals to read and write. So now let's look at a load word instruction to see what happens. So if I were to do a load word instruction, so when I do a load word instruction, this 22, register 22 is specified here. Okay, so this is your register 22, and this is my offset, minus 50. Okay, and my register destination would have selected this as my write back register, correct? My register destination would activate the multiplexer to select that this should be my RT register, which is 21. So the multiplexer will select this selection to go to my write register, correct? And then what will come out here? So your 16-bit instruction will go through sign extension, come here, and your multiplexer ALU source will select this as your ALU input, correct? Okay, and this is actually your register 22 data. So whatever is inside your register 22, and your ALU control would have told it to do a add operation. Your ALU control will have told it to do add operation. So this final address that come out is your register 22, okay, plus your offset of minus 50. So register 22 already has a 32-bit value, correct? 0x something. So that you add with a minus 50, that give you the final address, correct? A final address to do a memory read. So a memory read would have been activated. Then what will happen? You would have taken the data out here, correct? Data would have been activated and then available on the data bus of your memory. Okay? Then the last stage, so we are still in stage 4, correct? The memory access stage. The last stage is the stage 5, which is the memory write back. Okay, we will see that in a while. Okay, so in stage 4, for a memory load instruction, what you have is, you have completed the address calculation, you have activated the memory, and the memory is now available on the data bus of your memory system. If it was a store word instruction, what would you have done? It is the same thing, except that now the data is in your register 21 here. Okay, so you can see here that there are two things that will happen. You now need to have a RS here, and this is your RT here. Okay, so for a store word instruction, you need to read data 1 and data 2. Okay, which is slightly different from your load word instruction. Okay, for your store word instruction, this will come here and this will also come here. Okay, but your multiplexer here, which is not shown here, will still select this to go through. Okay, but there's another hard wire here to come in to directly connect. Okay, so what is happening here? So two things are happening. Your multiplexer will still select the immediate value to calculate your 22 plus your offset. Correct? So this is your ALU control telling the add operation, and this is your register 22. But since this is a store word, that means you are trying to do a write operation, your memory write will trigger. So when a memory write is activated with the address, then whatever data is presented will go into that memory region here. And this memory and this data come from where? This data come from your register file, which is from 21. So when I do a store word, your RT is not channel. Okay? So in your load word, your RT is channel here. Okay? But in my store word, my RT is channel here. Okay? So your multiplexer, okay, even though it select, okay, even though it will still select, even if your register destination is 0 or 1, does it make a difference? Okay, when I do a store word, if my register destination is 0 or 1, does it make a difference? It will not make a difference. Why? Because your control block will not activate this. If my control block does not activate my register write pin, it does not matter what I write over here. It's insignificant, correct? The write register and write data will only play a part if my register write pin is activated. But my control block will know that this is a store word instruction, so the register write will not be activated. So even if the same bits are copied there, it does not matter. It makes no difference. Okay, your control bit will now play a part to decide whether the register should be updated or not updated. Okay, so I know it's a lot to take in. Some of you may be thinking of a lot of funny things. Okay, but don't worry. I always tell my students there's always light at the end of the tunnel, but you must get through the tunnel first. Okay, so don't worry. We will stop here today because I foresee a lot of questions from a lot of you. Okay, so don't worry, don't worry, relax, don't be stressed. If you don't understand, it is normal. If you don't know what's going on, it is normal. If you are blurred, it is normal. Okay, what is important? You go for tutorial, okay, you try to throw a smoke bomb, get your participation point, okay, and then you wait for tutorial solution, and then you learn how it works. Okay, so don't worry, it's normal. Okay, you got question, come down, ask me please, okay. Depending on the opcode and the function field. So if let's say in a sense that this instruction where you need write back to register, If it's, for example, a store word instruction, then there's no register level, right? Then your register level will become different. Yes, even if there's some bits there, some value there, it's correct.
I've got two questions. This is the dumb one. What's the one with the ratio thing? Like 20 ratio 60?
No, it's not ratio, it's a bits. 25 to 21 means bit 25 to bit 21. Your instruction is 32 bit, correct?
Oh, okay. I don't know already. Sorry. I saw already.
So you're telling, because you know the first 6 bits is opcode, correct?
Yeah.
So first 6 bits is 31 to 26. Bit 31 to bit 26, that's the first 6 bits. Then the next 5 bits, the next 5 bits. So that is actually the bit location.
Alright. Okay. Another thing is that you just now say about the store word thing, right? You say some. I can't really understand that part. You say about the right, register right. Is this slide right here?
So basically what I'm saying is, if I need a store word, right,
Yes.
I'm taking the data in the register, putting it here. Right? So my in this case, my RP will come here, okay? And at the same time will come here, right?
Yeah.
Okay? So if I look down here, here also it comes here and here, right? Okay? But I do not need to worry that this register is being read because over here, both enemy stores will know that I'm going to instruct this. Yeah, the value is still there, but we are going to I'm not discarding, we're going to ignore it.
Not for now, unless it's store word, then it's sent to write data in the data memory.
So you must think of it this way that the data is traveling everywhere all the time. Then I must have my correct control bit to decide which data I'm interested in and the interested data where should it go.
So all the purple text words, right? All of the control bits. Okay. So store word doesn't activate the register, right?
No. Because store word is to take the data in the register already and
How about load word? Also don't.
load word is to read from memory. So I need to read from the memory. So after I get the final address, I take from the memory and then there's still one more stage which we will discuss tomorrow. That is the write back stage.
Okay, so but I said register, right? Would it be?
Yes. Because load word is reading from memory and writing back to a register.
Yeah, that makes sense. Okay. Thank you.
Yeah, I mean when you say 32 bit means it's 4 bytes. So each time you access a particular function, you will actually be reading and writing 4 bytes at a time because it's a store word.
So why does it start from 0 and not keep on to 15? That is
So because that is the instruction encoding, right? The instruction encoding is The one is that the one that we set reserved for the type A. Then after okay, so this one is the maximum one is side B, is it? Yes. Where's the remaining one? Oh, okay. Then why I say more time? Because 6 bits inside a side here, then remaining is 5 bits. So this 5 bits can have any combination. Now this 6 bits can have any combination, subtract the one that is reserved for this. Oh, okay. Okay, so basically, okay, so if you see down here, for example, now I'm at 100. Okay, let's say now I'm at 104 already. So the 104 come over to here, right? Okay, so 104 is moving, right? This is the address I'm moving, right? But this hardware will only generate a new one. So the in here, which is here, is already 108. Okay, but my PC over here is 104. Then in the next construction, what happens? The 104 instruction will be read out, and then the 108, we need to instruction at the address 104. Will be read off from here and sent to the processor. While the 108 will be copied from the in over to the PC. No, so the idea is to understand that even though this thing changed, okay, the instruction, so you see,
So you are just saying that every time we execute the run, we are actually at the next bit.
yes,
Like we are not at PC, we are at PC plus 4.
yes,
It's because we reach that counter first while it's still executing.
yes, correct. The adder block is very fast.
That's why every time like the QT string when we execute, right, they straight away go PC plus 4, but the result then just
Correct.
that's the yeah, then
That one is the one is the one that is over here, the reserve for type A. So you reserve one of the 6 bits generation for type A. So in this, you can only have 2 of which subtract that one. Yeah, that is the final one because you already have one here. This minus one is because you don't do a multiplier. So I need to subtract one before I multiply because that one combination cannot be included. Because that one combination is only zero for type A. Correct, but the upper 6 bits cannot. So the upper 6 bits, the actually doing subtraction. Right? And if the ALU operation you're doing is going to take more functions, then of course,
Also, there could be a difference in.
it could be different, but we do not factor in, like we just say it's negligible.
And you say that in zero is used for operation. Branch instruction. So they do this instead of checking that the result is zero. Is it because the ALU will give out the is zero faster?
I mean, in a sense, you can say that you do not want to be dependent. I mean, since you know that this equal or not equal is used quite frequently, so we will straight away use that is zero instead of decode zero. Because if zero is a single bit. So it's easier if I look at zero bit.
So it's worth adding the one more line and additional instructions just so that you can only